purpose of this video is to go over section 4 of chapter 3, and we will be talking about linear inequalities. In this video, we are going to introduce the idea of interval notation, which is another way to express a solution of an inequality. We are going to use that to solve linear inequalities and also to solve a special type of linear inequality called a compound inequality. So let's get started with interval notation. Now, when we are dealing with inequalities, the solution will not be a point on the real line. Instead, it will be an interval on a real line, and therefore it is important to understand how to express those intervals. And there's three ways to express them. One is algebraically, which is something you've probably seen before, such as the interval of all values of x between a and b can be expressed like this. Also, an interval notation, which is basically a shorthand of algebraic notation, and also the graph. Now, one of the things that you want to notice is that in algebraic notation, the first letter or the first number is always a smaller number, and the second number is always a larger number. The same thing applies here and here. Furthermore, notice that if you have a strict inequality, this is the less than or equal to sign, we have a parenthesis. And if we have a non-strict inequality, such as right here, we have a bracket. So this right here is the open interval between a and b. In interval notation, it is expressed as parenthesis a, comma, b, parenthesis. And notice in the graph, it is a line between a and b. And if we have parentheses in the interval notation, we have parentheses in the graph. Now also notice that these intervals are called open intervals. So if you have an interval where we have a strict inequality on the left-hand side and a strict inequality on the right-hand side, then this is called then that interval would be called an open interval. These intervals right here, where we have a non-strict inequality, are called closed intervals. Now notice that if we have a non-strict inequality in algebraic notation, we have a bracket, or actually, a bracket in interval notation. Non-strict inequality, bracket, non-strict inequality, bracket. And it turns out that these intervals are called closed intervals. These are the intervals from A to B, and it includes A and it includes B. Here, A is not included. You can get as close as you want, but you can never reach A, and B is also not included because you can get close as you want, but never reach B. Here, you can get all the way up to 3, but you can never go beyond 3. It closes at 3. And here, or negative 3, here you can get all the way up to 5, but you cannot get beyond 5. And accordingly, it closes at 5. So if you have a compact interval, and all these intervals are compact intervals because they start at a number and they end at a number. If you have a compact interval, then if both sides have brackets, they are closed intervals. If both sides have parentheses, they are open intervals. In this slide, we have a collection of intervals, which once again are bounded intervals. They don't go all the way to either of the infinities. However, notice that the relational symbols are slightly different. Here we have a non-strict inequality and we have a strict inequality. As before, if the algebraic notation looks like this, x is greater than or equal to a but strictly less than b, then for the interval notation, the non-strict inequality maps to a bracket and the strict inequality maps to a parenthesis. But notice that these intervals are not open and they are not closed. Remember, for it to be an open interval, this would have to be a parenthesis. For it to be a closed interval, this would have to be a bracket. So we could say that these intervals are half open, or we could say they're half closed. What we like to do in mathematics, we like to be optimistic about things, so we say that these are all half open intervals. For example, here we have x is greater than or equal to negative 3, but strictly less than 5. This right here would be the algebraic way of writing that. If you're asked to write that in interval notation, you would have the non-strict inequality. We would have a bracket over here. We would include the smaller number, negative 3, comma, the larger number, 5, followed by a parenthesis to correspond to the strict inequality. Almost got myself backwards there. And then once again, the graph, well, the graph is going to be a line between 3 and 5, and the symbols just basically follow over. So these are bounded intervals, and these are bounded intervals. Since we have all parentheses here, these are open. Since we have all brackets here, these are closed. Since we have a bracket on one side and a parenthesis on the other, these are half opened. The next collection of intervals are unbounded intervals. Notice here, these are intervals whose graph will go all the way to one of the two possible infinities, either positive infinity or negative infinity. In algebraic notation, you know that simply as x being greater than a. The interval notation for that is going to be the open interval from a to infinity. Now notice that since we have a strict inequality here, we have a parenthesis. And also, notice that next to the infinity, we also have a parenthesis. Why is that? That is because infinity is not in the real line. You can never, ever, ever reach infinity. You can get arbitrarily close to infinity, but you can never reach it. So whenever you have an infinity or a negative infinity, you will always have a parenthesis. As a consequence, this is an open interval, as well as this is an open interval. Similarly, down here, we have that x is strictly less than 5. Once again, since we have a non-strict inequality, since we have a strict inequality, we have a parenthesis here. And since we have one of the infinities down here, we have a parenthesis here. And so notice that if we're looking at all numbers that are less than 5, that's going to be all the numbers all the way down to negative infinity, or as close as we can get to it, all the way up to 5, but not including 5. And that's what that graph will look like right here. And once again, since we're talking about negative infinity, you can never reach negative infinity. You can get very close to it, but you can never reach it. Accordingly, we have a parenthesis here. So this is also an open interval. And then the last, and also notice that since these go to either positive infinity or negative infinity, these are called unbounded intervals. And these are the last collection of unbounded intervals. Notice how we changed the strict inequalities to the non-strict inequalities. As a consequence, the symbol about the a in interval notation changes from a parenthesis to a bracket, and to a bracket here, and a bracket here and here as well. Accordingly, in the graph, we use the exact same symbols. So if we have a bracket next to the a, we have a bracket here, or a bracket at -3, or a bracket at b, or a bracket at 5. Also notice that in interval notation, we have one side has a bracket, the other side has a parenthesis, because it's an infinity, and you always have a parenthesis associated with the infinity. Accordingly, these are half-open intervals. Now, when you are trying to solve inequalities, simple linear inequalities, your answer will always be an unbounded interval. It will either be a half-open interval or it will be an open interval. When you are solving compound inequalities, your solution will almost always be a bounded interval. It may be half open, it may be open, or it may be closed, but they will be bounded intervals if we're dealing with compound inequalities. So that's pretty much all I want to say about interval notation and algebraic notation. In your homework, you'll be asked to express some solutions in algebraic notation and other solutions in interval notation. It's important to understand which one is which. Maybe we'll talk about that in a couple of examples. The first thing I want to talk about is graphing inequalities, and we're going to do this through examples. And this example hopefully is relatively straightforward. Consider the following inequality. X is strictly greater than 7. We want to graph the solution to that inequality. Well, first notice that we have a strict inequality right here. So accordingly, the symbol in the graph is going to be a parenthesis. So it's going to look like that. And notice that we're looking at all numbers starting at 7. Let's say 7's right about here, going all the way to infinity. So we want to basically have a nice little thick line, as thick as my little pen here can make it. and then we are going to want to have a parenthesis here. Okay, so that's what the graph looks like. Now, how would we express this in interval notation? Well, notice that we are going to go from 7 to infinity. Since you can never reach infinity, we actually have to have a parenthesis here. Since we have a strict inequality, we actually have a parenthesis here. And what kind of interval does this represent? Inequality represent? Well, keep in mind, there's only 3 types. It can either be open, it can be closed, or it can be half open. And in this particular case, it is an open interval. Okay, let's move on to the next example. And I forgot to change that to a 1.2. Shame on me. Okay, so let's consider the following inequality. X is less than or equal to -4. So since notice here we have a less than or equal to sign. So we are going to have a bracket. One of these 2 brackets. It's going to be this one. So notice here we're going to start at -4. And we're going to go all the way down to -infinity. Okay? And since we have a non-strict inequality, that implies, let me get that on -4, that implies a bracket. So that's what that's going to look like. How would we express this inequality in interval notation? Well, notice we are starting at -4 or -infinity. And we are going to go all the way up. So all values of x less than or equal to -4. So we're starting at -infinity. We're going to go all the way up to -4. Once again, you can never reach -infinity. So we would put a parenthesis here. And since we have a non-strict inequality, we have a bracket here. What kind of interval does this inequality represent? Well, this is going to be a half-open interval. We could also say it is unbounded. And I kind of forgot that detail in the previous slide, so let's go back there. We could also say that this interval is also unbounded. Okay, and I have a hard time updating my little numbers here. Sorry about that. That should be 1.3. So here we want to consider the inequality from -4 to 3. So we want to graph the solution to this inequality. Well, notice here that I have a non-strict inequality. That implies that there's going to be a bracket. There's also a non-strict inequality here. That also implies it's going to be a bracket. Notice here that for the graph, we're going to start at -4. We're going to go all the way up to 3, which is right about here. Okay, since we have a non-strict inequality there, we have a bracket. Since we have a non-strict inequality here, we have a bracket there as well. Okay, so that's the graph. How would you write that in interval notation? Well, notice here, bracket at 4. Let's do it the way that we did it before. We're going to go from -4 to 3. Notice that we have a bracket here, bracket there, bracket here, bracket there. And what type of interval is this? This is a closed interval. And it is also bounded. Since it does not go to either of the infinities, this is a bounded interval. So that is everything that I wanted to talk to you about relative to interval notation and how it relates to algebraic notation and the graph of a particular interval. And of course, we'll touch on that later when we do a few more examples. Now we want to chat about linear inequalities. And notice the one thing about linear inequalities: they look just like linear equations, just without the equal sign. Instead of having equal signs, we either have strict inequalities, strict less than, strict greater than, or non-strict inequalities. And that's what we have. Okay, great. How do we solve them? In solving linear inequalities, we have the exact same goal. We want to isolate x to one side of the inequality and everything else to the other side. And then we want to determine which interval, or in some case, which intervals, would satisfy that inequality. And that right there is the primary difference between solving an inequality and an equation. In an equation, particularly a linear equation, you're looking for exactly 1 point, assuming that point exists. It's either 1 point or it's going to be the entire real line or nothing at all. Here, it is going to be an interval. If it is a simple inequality, it will be an unbounded interval. If it is a compound inequality, it will either be a bounded interval or possibly a disjoint interval. You probably won't see that in this particular course. Now, how do you do that? Just like in equations, any way you want. You have the available tools, which are combining terms, using the addition principle to move terms around, and then finally using the multiplication principle to remove coefficients. And sometimes you can also use the distributive property. Now, the one primary difference between when dealing with inequalities is the fact that there's a certain special rule that you need to follow if you are going to use the multiplication property with a negative number. And what is that rule? You have to change the direction of the inequality symbol. For example, suppose that we know for a fact that -3 is less than 4. Okay, well, what if I multiplied both sides by -1? Well, if I multiplied both sides by -1 and I did not change the sign, I'm going to have, let me get my pen back up here, I'm going to have that 3 is less than -4. Is that a true statement? No, it is false. To make it a true statement, you actually have to change the direction of the inequality symbol. And that's what we have here. So another example, suppose we have -2x is less than or equal to 6. Well, to solve this, what I probably want to do is to multiply both sides by -1/2. And if I do, I need to change the direction of the sign to preserve the inequality. And that and my result is going to be x is greater than or equal to -3. Does that make sense? Well, yeah. If x was -3, then I would have -2 times -3, which is equal to 6, which satisfies the inequality. Now, if x was, say, less than -3, say -4, -2 times -4, that is going to be equal to 8. Is that less than or equal to 6? No, it is not. So, which is once again why you need to flip the sign. Of course, -2 times -2. -2 is greater than -3. That is 4, which is less than or equal to 6. So that works out just fine. So remember, when you multiply something by a negative number, you have to reverse the direction of the inequality. There's also another rule that says that if you take the reciprocal of both sides, you also have to reverse the direction of the inequality, but you don't need to worry about that in this course. Okay, so inequalities and equations have a lot of similarities. Basically, the approach is the same. We are trying to get x, or the variable, on one side of the inequality or equation, and all the other stuff on the other side. That's what we're trying to do. However, when we're dealing with equations, we are looking for a singular point. When we're dealing with intervals, or inequalities, we need to find an interval. Okay, and also with equations, I mean, it's an equal sign. It's kind of symmetric. You don't need to worry about the direction of the equal sign because it has no direction. However, here, we have to pay attention to the direction and make sure we flip the direction whenever we actually are multiplying it by the negative number. And also remember, the arrow, the direction of the inequality, it always points to the smaller number. So we have 3 and 30. The inequality should always be pointing towards the 3, or if it's -30, the inequality should be pointing towards the negative. Again, always the smaller number. All right, and as I mentioned before, solving inequalities is just solving linear inequalities. It's just like solving equations, almost. We simplify it, or the approach is still the same. We simplify it by combining like terms and removing grouping symbols using the distributive property. We then use the addition property of equality to move all the terms with variables to one side of the inequality and everything else to the other side of the inequality. We remove the coefficient using the multiplication property of equality. So if you have a 2x, just divide both sides by 2. However, if you're multiplying by a negative number, that's when you got to pay attention and make sure you flip the direction of that inequality around. And then finally, you really need to check And the reason why you want to check is to make sure you got the right interval. And usually the best way to do that is to pick a number, say x equals 0. It's usually the easiest thing to compute. And then see if that number, and then see if that statement is satisfied by the inequality. In other words, that the inequality is true and if it's supposed to be true, or not true if it's not supposed to be true. And let's see if we can bring a few of these things home with an example, with some examples. Okay, so here is our first example. Here we want to solve the inequality 2z is strictly less than 14. Okay, so we want to solve that linear inequality, and we want to express our answer in algebraic notation. Okay, so let's start off with this. We have 2, so we can start off by writing it down. 2z is strictly less than negative 14. Now, we don't need to do any simplification. We don't need to do any addition because the one term, the z in it, is already over here, and the other term is here. The only thing we have to do is get rid of the coefficient, and that requires us to use the multiplication property. And what we're going to do is we're going to basically multiply both sides, or divide both sides by 1/2, or divide both sides by 2. I want to divide this by 2 to make the coefficient 1, and I'm dividing by 2 here. I need to divide by 2 here. And if I do, these cancel. I have z, and then z, and then over here I have negative 14 divided by 2. That is going to be negative 7. Since I'm dividing by a positive number, the direction never changes, and this is my solution. Does it make sense? Well, let's suppose z is equal to 0. 2 times 0, is that less than negative 14? No, it is not. That's what we would expect, so it does make sense. So here, our solution is going to be all values of x that are strictly less than 7. All values of x that are smaller than 7. So our inequality is going to point to the x, and it's going to look like this. This right here is algebraic notation. If I asked you to write this in interval notation, it would be negative infinity to negative 7, parentheses on both sides. Parentheses because of this, and parentheses because it's negative infinity. But once again, we were asked for algebraic notation. That's interval notation. Okay, how would you graph that? Well, we notice here we're taking all values from 7 and going negative 7. That's not negative 7, that's negative 5. Let me see if I can fix that. We are taking all values that start at negative 7 and go all the way down to negative infinity. So it's going to, and notice that we have a strict inequality. That implies a parenthesis. So that's what it should look like. Okay, well, here is our next example. This one's a little more complicated. Consider the following inequality. 4z plus 6.1 is strictly greater than 43.7 minus 4z. Just had to do decimals, didn't I? Okay, so here we want to solve the inequality for the given variable, which of course is z, and we want our answer in interval notation. Okay, so let's go ahead and do that. Let's start off with our equation here, with our original inequality. That is 4z plus 6.1 is greater than or equal to 43.7 minus 4z. Now, there's really nothing to simplify because we have no like terms in this side and we have no like terms on this side. So we need to go straight to addition, or to the addition property of equality. And remember, in the addition property of equality, what we want to do is you want to do those additions necessary to get all the terms with the z on one side and everything else on the other side. And now, when we are solving these things, remember, if you are dealing with inequalities and you have to multiply it by a negative number, you need to flip the direction of the inequality. Of course, now, if you move the terms in such a way that the coefficient is positive, you don't need to worry about that. And basically what I'm trying to get at is that we want the z to have a positive coefficient, so we don't need to worry about flipping this. So with that in mind, I want this negative 4z over here, and I'm going to do that by adding 4z, by adding this 4z to this side of the equation, plus 4z. And remember, what you do to one side of the inequality, you have to do to the other side. So I'm going to add 4z here as well. Okay, now since I'm going to have all the terms of z over here, I want all the other terms over here, which means I want that 6.1 over here. I can do that by subtracting 6.1. And if I'm subtracting 6.1 here, I want to subtract 6.1 on the other side. And now I can add all of this vertically. Over here, I have 8z. These will cancel. 43.7 minus 6.1 becomes 37.6. And of course, these cancel. And I still have my less than or my greater than or equal to sign. All right, now I need to get rid of the 8. And of course, for that one, I will use multiplication, the multiplication property of equality, or in this case, more like division. And I'm going to divide both sides by 8. I'm going to divide by 8 here. I'm going to divide by 8 here. Accordingly, these will cancel, and I am left with z. And notice that since I made sure that these are positive, I don't need to worry about the direction of the inequality. It's going to stay in the same direction. It's going to point in the same way. And it turns out, I can't do this in my head, but I do have a calculator, and it turns out that 37.6 divided by 8 is 4.7. Okay, and that would be my answer in algebraic notation. We need to write this in interval notation. Now notice that this is going to be all values of z which are greater than or equal to 4.7. So in interval notation, I'm going to start off with my lowest number, which is 4.7. And I'm going to go as high as I possibly can, which of course will be infinity. Okay, now since we cannot have a bracket next to an infinity, we need to have a brace. I mean a parenthesis, not a brace, that's for sets. And since we have a non-strict inequality here, well, non-strict inequality implies a bracket. So this right here is your answer in interval notation. And then how do you graph that? Well, notice here we're starting at 4.7. Let's say that's 5. Let's say 4.7 is right about here. We're going to go all the way up to infinity. There we go. And once again, since we have a bracket by the 4.7, I have a bracket here. And there you go. Our last topic of conversation is going to be compound inequalities. And these are examples of compound inequalities. That a, b, c, and d be real numbers, where a is not 0 because if a is 0, it's not really all that interesting. And then these right here are compound inequalities. And here we would have the expression ax plus b is greater than c, and ax plus b is less than d. So this is kind of like the intersection of two. It's like the intersection of two intervals. And of course, we can have strict less than. We can have less than or equal to, and also various combinations. But these are all called compound inequalities. The big question is how do you solve them? Well, the way that we solve them is we want to isolate x, or whatever the variable happens to be. However, we do not want to isolate x here or here. We want to isolate x in the middle. So when I think about solving compound inequalities, I think about the game monkey in the middle. I know what you're thinking. I don't get out too much. Okay, but that's pretty much what we want to do. We want to isolate x in the middle. Whatever you do on one side of the inequality, you need to do on the other two sides of the inequality. So whatever you do here, if you actually want to subtract b here, then you need to subtract b here and subtract b here as well. Okay, so there's basically three sides there's basically three sides to this, kind of like a little triangle. And what you do to one side, you do to all the other two sides. Okay, so let's see what this looks like. Here is our next example. So here the inequality negative 12 is less than negative 2z minus 2, which is strictly less than 2. We want to solve this inequality for the given variable, which happens to be z, and we want to express our answer in interval notation. Okay, so let's start off by writing this down over here. We will have negative 12 is strictly less than negative 2z minus 2, which is strictly less than 2. Okay, so the very first thing we want to do is we want to use the addition property so that all the terms with a z in it are stuck in the middle, which basically means, and all the other terms are somewhere else, okay? Which basically means you want to use the addition property to get rid of the negative 2. And we can do that by adding 2 over here. Once again, if I'm adding 2 here, I need to add 2 here. And I need to add 2 here as well, okay? Doing that math, I have negative 12 plus 2, which is negative 10. Okay, these cancel. The direction of the inequality does not change. And then over here, I have negative 2, well, I have 2 plus 2, which is 4. Okay, so let me bring that over here. Negative 10 is strictly less than negative 2z, which is strictly less than 4. Okay, now we want to do multiplication. Because we want to multiply this entire thing by whatever we need to make this coefficient equal to 1. Specifically, that means that we want to multiply this by negative, or no, we want to divide this by negative 2. If we're going to divide this by negative 2, we need to divide this side by negative 2. And we need to divide this side by negative 2. Okay, cool. Over here, negative 2 divided by negative 2 is just simply 1, so we are left with z. 4 divided by negative 2 is negative 2. Negative 10 divided by negative 2 is 5. However, notice since we divided by a negative number, the sign, the direction of the inequality needs to switch, which means we're going to have 5, which means instead of pointing towards the negative 10, it needs to point towards the z. And similarly, this needs to point, we need to change the direction of this as well, and this is what we have. Well, let me get my, and so here we have z is less than 5 and greater than negative 2. Now you might look at this and it might look kind of weird to you, but what you can do is you can take this entire thing and you can just write it in the reversed order. We can write this as negative 2. Make sure that thing is still pointing towards the negative 2. Is less than z. And once again, we want to make sure that it's pointing towards the z, which is less than 5. Okay? Now, what will this answer, and the reason why you want to do this is because when you write something in interval notation, you always want to start with the smaller number. This is the smaller number. Smaller number is negative 2. Okay? Now, you can work with either of these, you just got to be a little careful here. Since we have a strict inequality with a negative 2, that is going to be a parenthesis. The larger number is 5. Once again, since we have a strict inequality, we have a parenthesis, and that is the answer in interval notation. Actually, and now the next part is to graph the solution. Of course, that is pretty straightforward given the fact that we have this interval notation. We're going to start at negative 2. There it is. And you go all the way up, well, in a sort of a straight line, all the way up to 5 right there. Since we have a parenthesis by the negative 2, we have a parenthesis here. Since we have a parenthesis by the 5, we have a parenthesis here. For our last example, we have to deal with a fraction. Sorry about that. Okay, but what we need to do is we need to solve the linear equality for the given variable, which once again is z. We want to express our answer in interval notation. So let's go ahead and do this. Now notice that the first thing we want to do is you want to get rid of the fraction. Because fractions are evil. All right, to do that, we are going to multiply the entire thing by 2. Okay, and if we do, we are going to have 2 times negative 11 is strictly less than 2 times 3/2 z, which is minus 2 times 5, 2 times 5, which is strictly less than 2 times negative 2. Doing the math, we will have negative 22 is strictly less than 3 times z minus 10, which is strictly less than negative 4. Okay, now we need to do some addition to make sure that they get the get the term of the z by itself in the middle. So we're going to use the addition property of equality, and specifically we're going to add 10 to this to make this go away. Well, if we're going to add 10 here, we need to add 10 here, and we need to add 10 here. Using vertical addition, we will have negative 12. Negative 22 plus 10 is negative 12. These will cancel, so we have that is strictly less than 3 times z, which will be strictly less than negative 4 plus 10, which is 6. Well, isn't that convenient? Let me rewrite that up here. We will have negative 12 is strictly less than 3z, which is strictly less than 6. And then we want to do multiplication to get rid of the coefficient. So what we want to divide this by 3. That will give us a coefficient of 1. Well, if we're going to divide the middle by 3, I need to divide this by the right-hand side by 3 and the left-hand side by 3. And if I do, these cancel the middle, and I just have z. That's what I'm looking for. Over here, I will have negative 12 divided by 3, which is negative 4. And over here, I will have 2. 6 divided by 3 is 2. So this right here would be my answer in algebraic notation, but we want interval notation. So what do we do? Well, to do our interval, we start off with the smaller number, which is negative 4, comma the larger number, which is 2. Since I have a strict inequality next to the negative 4, I have a parenthesis here. Since I have a strict inequality next to the 2, I have a parenthesis here, and that is our solution in interval notation. Notice it is an open interval from negative 4 to 2. Okay, how do we graph it? Well, notice we're going to start at negative 4. We're going to go all the way to 2. Negative 4, all the way to 2. Since I have a parenthesis at negative 4 over here, I'm going to have a parenthesis at negative 4 here as well. In my interval notation, since I have a parenthesis at 2 here, I'm going to have a parenthesis at 2 there. And that is the answer to this particular problem. And that is all I have for this particular section. I will have a follow-on video for this section to show you how to do some of these problems in Hawks, because the interface is a little tricky and you might want to take a look at that so you can figure out how to do the graphs without too much planning. So look out for that one. It should help you with some of the problems. And if you have any questions, please feel free to contact me. This is Bob Boyle, signing off.